Well, hello and welcome everyone to this latest JMP academic webinar, JMP for Teaching Statistics in Chemistry and Chemical Engineering. Today's webinar will be delivered by Academic Ambassador Volker Kraft. I'm Ross Matusalam, fellow JMP Academic Ambassador, and I'm just here to host today and field some questions in the Q&A as we go along. So today's webinar, just to give you an idea, is going to provide an overview of the use of JMP statistics software for teaching in chemistry and chemical engineering. So if you're new to JMP, you don't already use it or specifically don't teach with it, the webinar should give you an idea of whether JMP might be a good fit for your course or curriculum. And if you already teach with JMP, this review of JMP features should highlight some ways that you could potentially improve or expand the use of JMP in your course. Now, before we get going, I do want to encourage each of you to submit questions in the Q&A as we go along. Any question you have, big or small, go ahead and type it into the Q&A panel in Zoom. I'll be in there answering questions as we go, and then Volker should be able to take some questions live as well. You can go ahead and use the Zoom chat for general comments that you'd like to make to your fellow attendees or to us at JMP, but please do type questions that you'd like us to answer today into the Q&A, and that just helps us actually keep track of the questions and which ones have been answered already. So thank you for that. So with that, I'll pass it on over to Volker to get us started.
Thank you, Ross, and welcome, everyone. Can you see my screen, Ross?
Yep, it's looking good.
Okay, perfect. Let's go. And I have to say, I'm also excited presenting today's webinar, which summarizes several of my activities this March: a DOE training at the University of Ghent, a JMP demo about robust process engineering at the Ruhr University in Bochum, and co-teaching a course together with BASF at KU Leuven. So on the PDF, you see the key applications of JMP here on our academic flyer for chemistry and chemical engineering. And we will look into most of these during my teaching demos today. The demos and several useful links are organized in this JMP journal, which will be shared after this session. Putting this content together, I was guided by three main sources. First, the guidelines for undergrad chemistry programs by the American Chemical Society. Here is the webpage and the document. You also get the link on the journal, and I have the PDF download here. So this section is about requirements for lab courses. And we have the critical requirements, some normal expectations, and then also the extra mile. And looking at these recommendations or even requirements, we see that experimental design plays an important role. So not just making predictions and designing experiments, but also evaluating the effectiveness of a design. Another topic is making connections between the data and subject matter expertise through modeling. And statistics, so statistical methods using software, and I think really important, understanding the variation in data and understanding also uncertainty and experimental error. And also data visualization and telling a story using effective visuals is another topic. Second, we hear from our customers every day which problem-solving skills they need. So you can read about real-world problems and solutions in our customer stories on our webpage, and you can look at these problems here. Click on any problem which seems interesting, and you can read about the details. And if you're interested in the BASF KU Leuven collaboration I just mentioned, we also have a success story sharing the details behind this project. And beside machine learning, AI, process modeling, and also data management, the required skills also include DOE, statistical methods, and data visualization. So very much in line with the ACS recommendations. And third, we also hear about several challenges from our academic users. Curriculum gaps. There's also a study published in the Journal of Chemical Education also emphasizing that dedicated statistics courses are rare. So consequently, chemical faculty often need to incorporate essential statistical concepts within existing chemistry courses. And of course, that takes time. So adding machine learning and programming, and also new courses about AI or green chemistry. Basic statistics are often sacrificed. Educational resources are valuable, of course, like our statistical thinking online course, but often offered as a voluntary activity. And practical applications are key, as you all know. So combining relevant statistical methods, industry standard software, and applications tailored to chemistry. And using JMP software and resources, I think you can tackle all of these challenges. And I will try to show you how. By the way, if you are interested in an introduction to JMP software for maybe a new user, or an overview about all our resources, or any deep dive into a statistical method, please refer to our academic webinar library at jump.com/webinar. And with that, I would like to start with a first case. And this case is really about the basics of statistical thinking. We will have observed process data from a chemical manufacturing process, and we will start to explore the data, visualize the data to see what's going on, look into some statistical analyses, also look into variation and try to understand the variation in the data, and also look at uncertainty, and maybe a more advanced application is statistical process control and also process capability. So here's the situation. So we are producing a key chemical, and we are disappointed about a very poor yield. So we have 90 batches observed. We measured the yield 90 times, and we have all the process settings. What we know is what we want, and that's a yield of at least 80%. So this is our lower limit we would like to see. And here's a summary of the status quo. So you see the lower spec limit, and everything below is out of spec. So this should be avoided. The question is how? So what is related to the process yield, and what are the best settings to improve in this case, maximize the yield. So the process is complex. We have many axes, many settings, and one response, the yield. Don't worry about all the details here. We just have many axes, including temperatures and vessels and suppliers and so on, which can be changed to improve the outcome. And here are the data as a jump table. Let me arrange the windows a bit so that you can see it better. Yeah, so we have the response column, yield. These are measurements, percentages between 0 and 100%. And here we can see the distribution in a preview on the column header. We also have a binary response performance. So a batch was rejected if the yield was below 80%. And then we have all the settings. And settings include categorical variables like vessel size. So you see this green icon. So this is an ordinal, but categorical variable. And we also have several continuous variables like carbamate amount, water content, and so on. So let us start to explore the data and see where we are. So first of all, what about the quality? Are we meeting our expectations? We can already see it's not the case, but the full picture is given here about the process quality. So this is about understanding variation. And the left-hand side, we see the variation of yield in our data. And this is excellent to judge about the stability of the process. So we do expect normal variation, also called common causes, but we are not expecting any special causes, which are typically problems we should fix. So only if the stability looks good, it makes sense to ask the second question: what is the variability in our data compared to the requirements, the specification? And the specification is this lower spec limit, 80%. And the answer can be given by a capability analysis. How capable is the process to meet the external expectations? And here we see a non-conformance besides several indices I don't want to talk about today, but we see a non-conformance. So for our sample, we have a non-conformance defects above 15%, and for the population, we are expecting around 20% defects. So that's really bad. By the way, this interactive capability plot down here can be used by students to play around with these settings here. So we can change the mean. If we are able to improve the mean of the yield, we see how this changes the capability. We can also change the sigma, the spread, and see the effect. So this was created by the control chart builder. So if you think, how much time does it take a student to get this output? It can be easily measured. So the student has to open the Analyze menu and then under Quality and Process, start the control chart builder and then drag the variable you're interested in, and that's yield. And there you are. So we would need to add some colors, colored zones here, and alarms. Also this interactive graph we had to explore the settings. But that's it. Yeah, and I can click done, and you see everything you need to see in the first place. So that's quite easy using control charts. A second standard platform in JMP to explore data is our graph builder. So that's the main tool for data visualization, a very flexible tool. And let me also start this. So it's the first option on the graph menu. Yeah, and then I would say let the students play, and let them ask questions and try to answer them by data visualization. So I just dropped yield on this canvas in the middle here, and we get a dot plot. Yeah, we also see the good ones, the bad ones in green and red. The lower spec limit is also added to the graph. And then how does relate to some of our process settings? So for instance, carbamate amount. Yeah, I drag this setting, process setting to the x-axis, and then we get a scatter plot and also a smoother. Yeah, I could change the smoother and have some detailed settings on the left. I could even add a confidence interval to the smoother line. So we also talked about confidence and uncertainty. So this is probably helpful, but I can also replace the smoother by a simple regression line. Yeah, and we get a confidence band, the 95% confidence band for the fit. And we see that there's an upward trend. So the higher the carbamate amount, the higher the yield we can expect, at least following this very simplified model with a single predictor. Yeah, very, very simple. But it's just exploring what's going on, what we believe is happening, and just to confirm it or reject it and create more questions. Yeah. So there could be somebody saying, wait, this relationship is probably dependent on another setting, the size of our vessel. Yeah, so I can take this maybe here or here. I'm just moving this around on different drop zones to see what I get. And then I drop it as an overlay variable, because this tells me, let me just make it a bit bigger. So this tells me that the relationship between yield and carbamate amount is dependent on vessel size, and that this relationship has a negative slope for the medium size, but for the small and big vessels, we get a positive trend. So this informs me about an interaction between carbamate amount and vessel size. Yeah, so talking about one of these two variables doesn't really make sense without also mentioning the other. So they go together. And everything is interactive. So I could also check who's this guy here. Maybe seems a bit like an outlier. So I could see what it is. It's a row 89. Yeah, and if I want to maybe check this again later, I can also, oops, I have a problem with my mouse here. Okay. Yeah, so I can highlight it and then go to the data table, check it there, mark it on the data table, and then look at this later on. Graph builder. There are many more graph types you can create there, and we will see some more later during this session. Yeah, and then you start with statistical analyses in a univariate way. So this is really easy. analyze, and then you choose distribution. You then select the single variable yield, the response, and then you get this output, a histogram and some standard statistics, summary statistics. You can look at quantiles. And from here, you start to explore this variable further by checking normality. So nothing to worry about, looking at a normal quantile plot, maybe fitting distributions. Let's try all and see what's the best. Oh, best is normal to mixture. I change it to normal to look into the details for that distribution. I see the details down here. How good is this fit? There's a goodness of fit test there. I can just run, and then JMP uses these two tests, and the p-values are not that small to reject the null hypothesis, which is also mentioned down here. So that's a single variable. I can also look at distributions for multiple variables side by side, and then everything is connected. So I can just look at the rejected batches, and we see that the small vessel size is maybe not is maybe the best to protect against rejected batches. Or other way around, I can also multi-select the high yield batches, and then it's confirmed. So the small vessel size is best. Next step would be also on the analyze menu, not distribution, but look at two variables, one y, one x, and doing this for a continuous y and a categorical x. JMP gets us automatically into a one-way analysis of variance. And this is all about means. Also, the context menu in this situation is all about means and comparing means. Here we already have the results. So instead of looking at the details down here, I can also click a circle, and then by color, I can see which means are significantly different for these groups. By the way, every analysis can be saved to the data table as a JMP script. And this was done creating these scripts. So there was no programming done to have these outputs here. It was all clicked together and then saved as a script to the data table. And now I can run them again to look at the results. So there are also multivariate methods and a platform to look into correlation. So here we can also see the correlations by a colored map, or look at multivariate outliers. Again, if I want to maybe exclude these batches because they are above the upper control limit, so they can be suspicious and not part of the main data cloud, I can select them and then just have a special marker with them, and then I also see them on the data table with that marker. And finally, building a model. So that's often the goal, to have a model to generalize what we learn from our data and to understand what's happening. So this is the fit model platform in JMP. Also on the analyze menu, I can go back from this saved analysis. I can go back by relaunch this and see how this was generated. it was using the yield as the response. Why? We had these model effects on this list to analyze, and then standard least squares as the standard multiple regression modeling technique. And then clicking run, we get this result. And you can look at the ranking of model effects. So that's this effect summary. This is a great diagnostic plot. There's also an R-squared value of 74%, a very small p-value, looking good. And then we have the profiler, and the profiler is the place to understand what's happening, understand the relationships between the response and our process settings. So here we see, for instance, that we have a curved relationship here. So that's the quadratic effect of carbamate amount. We also have an interaction between base assay and reaction temperature. So to make our process maybe more robust against temperature changes, I can set this base assay and just use this interaction here if that's the goal of this exercise. So what can we learn here, just to summarize? All this statistical thinking and getting insights from data is supported in different ways. So it's very accessible. There's a direct interface between the data and the user, and just point and click, no coding required. All the there are many visualizations, but they are also interactive. And the workflow is a step-by-step discovery flow, unfolding just to answer another question with the next step. But you may also get a new question, and you will move on. Yeah, and all of that is supported by the context menus, which are a bit magic because they provide all the tools and platforms and the tools and tests. So everything which is useful in a specific analysis context. Yeah, so the user should think about the problem and be data-driven, not method-driven. Okay, so let us move on to a second example. So this is more about modeling and model evaluation, model comparison, but also predictive modeling, which typically requires to protect against overfitting. And validation is a best practice also built into all our modeling platforms. And here's the example. So we are creating a key chemical product, and we are using 5 ingredients. And the ingredients are a selection, so a selection from reactants, from ligands, bases, solvents. So we have to pick one from each group. And these are 5 categorical variables. Pick one from each. And that's a recipe. And then the question is, how good is the yield again? And this was measured and is available as a subset of all recipes. So if you multiply the number of levels, you get 4,608 possible recipes. But we have 150 combinations of factor levels in this subset. And we are going to use this to build a model, but then we will use the model on the big data set for all the recipes to predict the yield. Yeah, so what do we have here? We have the 5 categorical factors and yield as the response. And for validating, we have a validation column which splits the data into training and validation data. Yeah, so we could start to look at distributions. So high yield is good, as always. Yeah, so we see that this level here, CLQ, is not helping with high yield and some other insights, but we cannot really optimize the yield just taking the distributions. Graph builder. Yeah, we can look at yield against each factor, and the column switcher changes the factors, and we can explore all the factors, the 5 factors we have here, and draw some first conclusions. Believe it or not, this is also graph builder. We have just our 5 categorical factors nested. So here we have reactant 2 and then solvent. Here we have reactant 1 and ligand, and then we have base on the axis here. And yield is colored, and the darker green, the higher the yield. And all the white space are the other recipes which are not in this subset. We can check if there are some green zones or bad dark purple zones and may get some hints from those as well. And now we start with modeling to understand what's going on and what's driving the yield. A first model we could try is building a decision tree. And this is about predictive modeling. And I show you what was done here, launching this decision tree platform. I relaunched this analysis, and here we see we have the outcome, the yield, our response. Oops, we have our 5. Oops, we have our 5 factors down here, and we have the validation column used for validation, splitting the data into training and validation. Yeah, and because we have this, we also have this go button. Yeah, so instead splitting 1 by 1 and split again and split again. So this is just the first split. Yeah, and the factor which was used was reactant 2 to separate the data into high yield and low yield recipes. But I can also click go, and then JMP does 6 more splits, so 7 in total. Why 7? And this is great also to explain why to validate. And here we see that the blue training data shows that the R-squared would go up and up and up, but here we would start to overfit our model. And the red data are the R-squared on the validation data set. So we built the model using the blue data, but then we check the model, the R-squared on the red data. And when this goes down, then we stop to make the model more complex. That's the reason for choosing 7 splits. And then the question is, okay, for the final model, it's probably not a simple decision tree. For the final model, which model to use? Yeah, we can ask the JMP model screening platform to check out all models, all methods. And again, let me show you how this was done. It's also on the Analyze menu called Model Screening. So we just defined the problem again, same problem. We use the validation column again for validation, and we selected all the methods we want to try for this problem. And then by clicking OK, JMP applies this to all modeling methods and then presents a ranking. And here on the validation data, the winner is the neural boosted network. So this has the highest R squared. It also has the lowest error. And so that's good. Neural boosted, the winner. We can also look into diagnostics here. So these are the diagnostic data. So the actual yield by predicted yield, just look at the validation side here. And the more the data points follow this line here, the better, the higher the R squared. And if you compare this with a support vector machine model, so this is not that good, following the ranking as well. So neural network, that's it. So I can just select it. I can run this model. And here I take the model. I could also, I take the model and publish the model formula first. I close the model because I have the prediction formula in my depot. And from here, I can either generate Python code, C code, other languages to deploy the model in other environments. So this is an example for Python code. Or I run this model on another data set. And this was done on the other big data set with all the recipes. I close the subset and reality check. So this is really luxury that we have the measurements for all our data, all the recipes. That's typically not the case in the real world. So, and that's the reason why to build a model, to make the predictions. Here we can compare the predictions with the real measurements of yield. So these are the real measurements, and that's the predicted yield. Using this winning model, the neural boosted network. And I just want to show you this as a summary of the result. So this is the heat map with all the recipes. And the more red, the better, and blue is bad in this scheme. And this can be compared with the real measurements. And considering that we only used 150 recipes out of more than 4,600, it's a fairly good model doing a good job. Okay, enough about recipes. Just summing up. So all of this modeling, checking different models, comparing models, selecting a model, it's all easy and fast. It's very visual. So that means it's all very engaging for students and interactive. And it really helps to improve the process understanding and get better insights. One more, my third case today is about robust process optimization. So this also includes a bit of design of experiments. So we will have experimental data in this case, and we will look into simulation optimization in this example. So we have 5 factors. They are continuous in this case, not categorical. And a single response, again, percent reacted, and it should be maximized as well. And this is a very small data set. What's nice, because this has been used in an experiment, and it was a very efficient experiment with just 13 runs. We see it's a JMP design table, and the design was a definitive screening design, which can be created on the DOE menu, definitive screening design. And from the design tool, you also get some scripts automatically. So you can use later, and one of the scripts, the DOE dialog, can be used to go back to the design stage at any time. So here we see the response, percent reacted to be maximized, and a lower limit of 70. We have the 5 factor with their factor ranges, a lower and upper limit, and then the design preview. We also see that there are some midpoints. So a definitive screening design is a 3-level design. And we can look into some diagnostics like power or correlation between model effects before we actually run the experiment and collect the data. And if we are happy with the diagnostics, we make the table. And the table has some scripts, as I mentioned, but an empty response column. So this is before the experiment. So we have to take this into the lab and take the measurements. And now we are after the experiment with this data table. Now we can explore the data visually again. So here we can look at the measured percent reacted for each factor. Feed rate, is it important, significant? No. Catalyst, yeah. There's a bigger effect. It seems to be active. Stir rate, maybe not. Temperature, oh yes. Concentration, yes. Just the first visual inspection. No modeling yet. We can also look at all the factors side by side, and then come to the same conclusions that feed rate and stir rate are the least significant factors, and that for concentration, it's maybe a nonlinear effect. So having some curvature here could probably help. Distributions and so on. And then finally, we build a model. Here's the model. This diagnostic plot looks very promising. So we see a very small p-value, an R-squared of almost nearly 100%. And we also see that concentration, temperature, catalyst are the significant main effects. And we have one interaction and one quadratic effect. And all of this is visualized on the interactive profiler again. So here we have the curvature on concentration, and we also see the interaction between catalyst and temperature. So that's this interaction here. So now the question is, which settings give us the highest percent reacted, the best output? So for this, I use the automatic optimization. So we are looking for the settings which get us to the most desired spot. So in the landscape on the response surface, we want to get to the highest point, which means the maximum percent reacted. And for this solution down here, we have 81% as the highest yield we can expect following this model. Yeah, the highest average yield. And average means we also have a confidence interval, 95% in the blue and in brackets down here. So the good news is it's far away from the 70% lower limit. So we seem to be on the safe side. But is this the best solution? Yeah, so there's another strategy in JMP, and that's with the help of the simulator, which is built into the profiler. Yeah, and using the simulator looks like this. So here we have the same profiler, basically, but the simulator has been used to add some stochastic variation on our factors. So we cannot guarantee to always have the temperature set to, let's take the best settings, temperature set to 120. So here we have the maximum percent reacted again, but we expect some random variation. We also have some noise on the response here. And now a Monte Carlo simulation creates this histogram. And that's the distribution of output values from 10,000, 10,000 values. And this is the critical part, everything below 70%. So with this variability, we are not on the safe side anymore. So if we simulate here, we are around 4 or 5% of defects. So the question is, how can we improve this? And the answer is a robust simulation. And a robust simulation is a simulation experiment which can be executed automatically by the software as a simulation experiment on the simulator. And this leads to a different solution. And if we simulate again, we see that the defect rate dropped maybe by 80%, significantly. So this is much better if we want to get to a low defect rate. The price to pay, the response percent reacted is a bit lower. So we are not at the very maximum in our landscape anymore, but we are more sitting on a plateau, so more operating on a plateau, so that any changes on our factors should not let us drop rapidly on that surface. So that's a different strategy. It uses Monte Carlo simulation, a Gaussian process model behind the scenes. It's basically a space filling design to get there. Yeah, and then you can easily compare the different strategies. Yeah, highest or best output or most robust process. Yeah, and you can explain it, present it visually. Everything is linked, all the profilers and models. And all what you do, because this is a more complex workflow, all what you do is documented, reproducible, and changeable. And you can even record this as a workflow. So just to mention some other examples, and these are just teasers. Teasers about some more advanced applications, which are also provided by JMP Student Edition. Yeah. Student Edition provides all the capabilities of JMP and also JMP Pro. Yeah, and two of these here are Pro exclusive features you also get if you use JMP Student Edition in your class. I'm currently using 18.2, so that's a pre-release. So this version will be made available on my.jump.com for Student Edition users, so you can get an update probably during March if you're using 18.0 right now. So just 3 teasers, because we could talk about 4 hours on each of these topics. And we also have dedicated webinars and resources on the web. The first is a feature supporting quality by design, building product quality into the process, and do this quite early. And the feature here is the design space profiler. Let me just show you a quick example what this means. So here we have a chemical process again producing plastic. In this case, these are car tires. Yeah, and they have 4 responses, quality characteristics, and we have 3 ingredients, silica, silane, and sulfur. Yeah, and there was an experiment, and from that experiment we created a model, and here we have the profiler again for 3 factors, but 4 responses. And now we can also optimize and look for the best settings, maximizing these 2 and matching a target on the 2 other responses. So far, so good. So now there is a feature on the prediction profiler. I already showed you the simulator. So now I want to show you the design space profiler. And this is available here. So we have the simulator, sorry, the profiler again, not the simulator this time, but below we also have the design space profiler. And these are the critical results. So what we want is we want to improve and increase the in-spec portion. So assuming we have some specifications set on our responses, and these are the specification limits, and here we see with all our data, we are not in spec for all the outputs. Think about, there's a knowledge space, everything we know about this problem. Then we did an experiment. That was the experimental space. And now we are looking for the best control space. So the operating space, which gives us the highest in-spec portion. But we will give up some of our factor space, which is not in spec. And this can be done by following these visuals here. So if this curve showing the in-spec portion goes up, it's a good sign. And I can go up here, just making the lower limit for silica higher. And this improves the in-spec portion, but it also removes some data from the whole experimental space. So I can also add some other visuals, which are really nice to see what's happening. Yeah, so here we see all the data points. Red is out of spec, green is in spec. And we have the factors on the left and we have the responses on the right-hand side. Yeah, and now you see what's happening. So just by changing this, yeah, so we want to get rid of the red points and just keep the green points. Yeah, we can also do this automatically, yeah, by move inward, getting or keeping more green than red, and do this automatically. And if we proceed, we go up with the inspect portion. Yeah, we get higher and higher and higher. And then at the end, with just a few data points, a small control space, we get to 100%. We are just looking at 1% of all the data we have here, but let me go one more in, but just the good ones. And at the end, the settings we found here, the control settings, can be sent back to the profiler, for instance, as constraints. And now we are constrained to this control space where we will only have in spec outputs. This is following quality by design and using the design space profiler. Another big topic is functional data analysis. Here I don't have embedded data. This is just a data set I'm opening from the disk right now because we are looking at 1.5 million rows in this data set. So this is about nuclear magnetic resonance spectrography, it's an NMR data set, and the measurements are the Y's over the axis. And that's done for multiple labels, more than 230 different labels or measurements, and these are the curves we are looking at. So I can show you what I'm talking about here. So we have the Y and the axis for different labels. So these are the curves. And remember, we have 1.5 million data points, and we can still work smoothly with these visualizations. We also have a mixture of ingredients, propanol, butanol, and pentanol. And from the spectral measurement, we want to predict these portions, for these ingredients. And it's also an experiment which was used here, and I can show you how that worked. So using these three mixtures, so we can see all the measurements on this ternary plot, show just in 5% steps the measurements which were taken. And here is a result of a functional data analysis. It takes a few seconds to pre-process and also model and transform more than 230 curves or functions. And here we see that there's some pre-processing involved. So we have also spectral pre-processing options and special filters. So here we just reduced the data and mapped the data to a grid. And then we see the result here. and we have a mean function for all our curves. And we also see where we have the highest variation over X. And then we build models. Yeah, so here the modeling was done using wavelets. Yeah, and these are the results. And if you know principal component analysis, this is very similar. Yeah, but here we are talking about functional principal components. Yeah, and here we have all the components. They are weighted shape functions added to a mean function. Yeah, and the more of these shape functions we use, the more of the variation in our data can be explained. Yeah, so that means that we just need the weights for these shape functions, a small number of shape functions, and can explain the majority of the data. Yeah, different profilers. At the end, we get an FDE profiler again. Yeah, so this one can be used. So I can change propanol to see the relationship with the spectral measurements. So you see that the second peak from the left depends on propanol. Yeah, and you just by looking at this, you can learn more about this process. This is about analyzing functions. And for the third teaser, I don't have the time to show you an example, but you can get an add-in for deep learning from our marketplace. Here is the link, and we have the website here. So marketplace.jump.com, and then look for Torch Deep Learning add-in for Jump Pro, but it also works with Jump Student Edition. Yeah, and this gives you access to pre-trained models of the PyTorch package. So it also uses the embedded Python installation, but you get everything through a Jump interface. Yeah, and then you get outputs, typical Jump outputs, interactive. And here is an example of such a result. So here we have the model launch. So there was an image model because we used spectral images to predict, again, the propanol, butanol, pentanol. So a similar NMR problem. The hyperparameters which were set, and then the outputs. So the training history over 200 epochs, and then the details about all the models in Jump. That's using deep learning after adding the deep learning add-in to your Jump installation. Yeah, it's documented, it's available for free, it just needs a download and a double click. Okay, so wrapping up, that's quick, and we are already over time, so that's good. What we want by making all of these connections is creating benefits for all of us. So for our industry customers, they need a steady pipeline of skilled graduates. For teachers, we want to provide resources, expertise, and all the support you need to adopt Jump more in your courses. And for students, we want to help them enhancing their employability by bridging the gap between higher education and industry demands. And if you are a teacher who wants to engage with us and consider integrating Jump into your course and using some recommended resources, just talk to us. And here is a link, a QR code. We are happy to set up a short one-to-one meeting and help you getting started.